Now we come to the final component of hypothesis testing. You might wonder, why are we spending so much time worrying about this? Because later I'm going to tell you, don't worry about hypothesis testing as an individual test until we get to the control phase. But the reason I'm doing this is because all statistical tools and analysis fundamentally are based on the concepts of hypothesis testing that we've been talking about. So the last component of this is the actual tests of difference that we can use in terms of Minitab. So we're going to ask ourselves, what is the test of difference? What is it we're trying to discover? Now, we're going to also talk about false positives. When do we see a random difference appearing as if it was a statistical difference? And then we'll talk about three different types of tests. Tests of difference for means, or location, the average, if you will. Tests of difference in proportions, or the ratio performance, like number of failures per sample size detected. Or tests of difference in variation about the consistency of the process. So let's begin. I want to go back to some statistical reasoning. So statistical reasoning is saying, are things equivalent or aren't they? The fundamental tool for this is this idea of hypothesis testing. So statistical tests of hypothesis are based on a comparison to some unknown or known, if you will, or expected underlying probability distribution. So I have observed the real data versus expected data, the probability distribution. So we say it's a normal test. I take my data and I compare it to a known normal distribution. If I say it's a distribution that is Weibull, I compare my data to a Weibull distribution. If I say it's Erlang, I say it's my observed data versus the Erlang distribution. So anytime we have this observed versus detected, we are getting a test of statistical difference. So the goodness of the final test is based on the comparison of the level of risk and says, what is the level of risk? Is it acceptable, my risk of being wrong, either accepting a bad decision or missing an opportunity by rejecting a good decision? Statistical tests are going to be then probabilistic about the outcome. So the primary objective of a good analyst is to determine or explain something with numbers that expands the knowledge of the person who's making the decision. Now, as a statistician operating in the process, well, you might just call yourself a statistical engineer operating in the process. You need to be inherently skeptical of everything. Just because we see a p-value doesn't mean we jump on it. Okay. So these statistical tests are that. They're statistical tests. They're probabilistic inference. It's not a fixed statement about reality. So the ultimate test or the ultimate conclusion should be based on the physical knowledge of that real world and the processes and the process knowledge we have. So the net effect of finding a difference is more important than this actual calculation. If a difference exists, I see Bob, I see wow, I should think about this. Why? And we want to get back into the physical world and the rationale there. So tests of difference indicate something is statistically different, but it doesn't tell us about the practical differences or the practical value. And when there's not enough evidence, in other words, I don't have the p-value sufficiently small, to reject the null hypothesis, that doesn't mean anything at all about the validity of the null hypothesis. We never prove the null hypothesis. We either accept or reject the alternative hypothesis, and in so doing, we elevate the probability that the null hypothesis is true. So, when we reject the null hypothesis, we're declaring that the finding is of statistical difference. It's unlikely to be happening due by chance. Now remember, if the sample size is very large, that small statistical difference could actually just be statistical difference due to the enumerative analysis. In other words, we're using close to a population sample. And so it may not be real important in terms of the physical world, which is the physical confidence interval of that measurement. So we should actually use hypothesis testing as a filter before we start judging practical significance. So we're interested in both of these things being interpreted by ourselves. One is the statistical difference, and the second is the practical difference. Now, how do we do that? Well, one way we can do that is say, what is this idea of a false positive? So false positive is the distribution, statistical distribution, gives me a test and it says I have something that is outside the normal confidence interval, but actually it's really a part of this type of process. So we call this a type 1 error, the probability detecting something that is outside the confidence interval when the process is really in a state of control. And we see that this average run length, this is called, it's 1 over alpha. And if we take a look at this, if we have a X bar R chart, alpha is 0.0027. So 1 over 0.0027 means 1 out of every 370 observations, we would get this out of control condition, when in reality the process is not out of control. Now if I compare, that is my expected value, and if I compare the observed value, so if I take a look at, say, 400 sample sizes, and I see 10 out of control, that means it's 10 times, if you will, the probability of just a random occurrence. That's unusual. But if I see 2 out of 400, it's not enough to convince me we really have a change. So this comparison of the observed to the expected and the magnitude of the change, that's called the chi-squared goodness of fit test. And we can use this logic in making any comparison between observed data and an expected probability distribution. And when we talk a little bit about the normal probability distribution and the Anderson-Darling test, when we talk about residuals analysis, what we'll see is that's exactly the calculation that's being used there. Now, what we want to review is statistical reasoning is nothing really new. It's been going on for a long period of time. It's been based on different types of probability. Hypothesis testing is based about the population parameter, and I'm asking the question, is my sample like the population? The population is what you would expect for performance over a long period of time. And we start seeing this p-value is measuring the likelihood that the data I observed is like the expected long-term population performance. In other words, we're saying that this is due to chance or not due to chance. Now, the magnitude of the physical measurement may or may not be of practical importance, so we have to make that choice. Okay, so what are the tests? Now, there are going to be several tests that we are going to talk about here. One is a variable test. It's a one sample z test. And this is when we are having a sample size greater than 30. And so the idea is I'm saying, does this sample come from a normal distribution? So I can have a two-tailed test, in other words, it's above or below, or I can have a one-tailed test, it's above or it's below. So I can make those choices. Now we're going to have a little exercise that we're going to be giving you, and it's not going to be in the video, but it'll be in the textual materials accompanying this course, that allows you to test how that one sample z test actually works. The second type of test is a one sample t test. And the only difference here is rather than the normal distribution, we're looking at sample sizes less than 30. So this is using the student's t distribution. And here we can see also the difference that we would like to be able to detect. It's going to be two-tailed type of test. And so it could also be a one-tailed type of test, just like with a normal distribution. With attribute data, I can test a one-sample p-test. And here I'm testing the proportion of failure against some sort of confidence level that I would have success or failure designed into the process. In many old-time statistical methods, they used what was called AQL, or average quality level. And they say it was a 2.5. That says 2.5% of the products are allowed to fail. So you would test, is my sample above or below 2.5 based on the sample size, using this attribute data one sample p-test. For variables data or two sample tests, I can have a two sample t-test. So here I'm comparing before and after events. Or I can have a two proportion test and do exactly the same thing. Now, what we see is that this two sample t-test, we're going to generalize, and that will become what we see for multiple samples, a one-way analysis of variance. So we'll talk about this, and we'll see hypothesis testing is going to be built into the advanced statistical tools we describe. It'll be built into analysis of variance, it will be built into regression analysis, and it'll also be built into as a logical part of designed experiments. So hypothesis thinking is engaged in EDA, or exploratory data analysis, to determine the practical significance of rational subgroups. But hypothesis testing is actually proving the merit of the analysis. So if the sample is the same as performance, so one sample t-test, based on sample size, it could be a z-test. The sample is the same as historical performance. It's a one sample test, either z-test or t-test. Do two samples come from the same population? In other words, were they made the same way? Or was there a difference? I changed the process. Did it make a difference? Or we changed the design of something. We test before and after the design. That's going to be this two sample t-test. Or it could be a paired t-test, but that's very rare. Or we can evaluate, has the process consistency changed over time? And this would see as a test of equal variance. So when you go to this workshop module, you'll see in the notebook different examples of these, some sample data that you can test in Minitab to see how you actually do those analyses and test what your conclusions were drawn. There's also an instructive version that gives you the solution to those types of problems. So good luck on working them out.